Greetings, Precalculus students. I hope everybody's doing well. Today we begin a new unit in Precalculus. We are done with polar coordinates and polar equations, and now we are moving on to a brand new unit, sequences and series. Sequences and series, which will probably be our last unit of the semester, we'll see. But sequences and series is the unit that we're going to be moving on to. So you'll see this is a big part of this unit is going to be contingent upon your ability to recognize patterns, which I know even those who are not necessarily quote-unquote good at math are at the very least good at recognizing patterns. On the other hand, I know at the same time, recognizing patterns is not something that comes natural for some people. So for some people, it might take a little bit more time. For other people, this unit will feel a lot more natural to it. So let's get to our bell ringer, and then we'll get to the gist of the notes. Okay, so write the next two numbers in each pattern, assuming each pattern continues. Then write a rule for the nth term in each number pattern. All right, so first, find the next two numbers in each pattern. So for the first one, we have 1, 3, 5, 7, so on and so forth. So hopefully this one seems pretty obvious. It looks like the numbers are just going up by 2. So the next two numbers in this pattern, if we just continue this, would be 9 and 11. Okay, so that was pretty simple. So it looks like we're just adding by 2. Now, the next one says to write a rule. Write a rule. Now, there's a couple ways we can do this. One way we can think about it is, all right, to find the next number, so to find next number, add by 2. Okay, that's a very informal rule, right? To find the next number, we add by 2. Well, what if we wanted to find a rule that we could use to find any number on the list? So for example, let's say we wanted to find the 50th term in this list of numbers, the 50th number in this list of numbers. How can we try to find a rule that can help us do that? Well, one way to think about it is to try to break it down like this. Well, let's see. So the first number is 1. So this is the first number. The second number is 3. And then so on and so forth. All right, so let's see. First number is 1. Second number is 3. Now, it looks like we're always adding 2. We're always adding 2. And it looks like we're starting at 1. All right, so one way to think about this is, so we're going to use n. We're going to use n to represent our term number. So like our second term, our third term, fourth term, fifth term, so on and so forth. So that's what n represents. So if n is equal to 2, that represents the second term. If n is equal to 3, that represents the third term, so on and so forth. So it looks like we're adding by 2 every single time. So what we're going to do here is we're going to put a 2 in front of the n to represent that addition by 2 every single time. That addition by 2 every single time. And then, if you notice, each of these numbers, 1, 3, 5, 7, they are each, and 9 and 11, if we continue on that pattern, they're each one less than a multiple of 2. One less than a multiple of 2. One less than a multiple of 2. So, to translate that into a mathematical expression, we would write 2n minus 1. So 1 less than a multiple of 2. And a multiple of 2 is just 2 times something. A multiple of 2 is just 2 times something. So this would be our rule. So this is a more formal way to write it, 2n minus 1. And this was a more informal way to write it. Find the next number, just add by 2. So that is a very basic example of what a sequence looks like. Now, once again, for some of you, this might have been easy. For others, this might have taken a little bit more time. But there is, as we move through this unit, you will see that there are steps that you can take to ensure that you get this equation, even if being able to recognize the pattern right away is not obvious. Now let's look at number 2. Number 2 is going to be a little bit trickier. So it looks like this adds by 3, this adds by 5, this adds by 7. Well, so it looks like the next one should add by 9. So whatever that next number is should add by 9. So that means if it adds by 9, the next number is 26. And that means the next number should add by 11, which would mean that the next number is 37. Okay, so this one's a little bit trickier. Now, a little trick to recognize for a pattern like this is if you notice, so the differences between each numbers always increases by 2, right? So the differences between each numbers always increases by 2. So that'd be a very informal way to think about it. So the differences between each number always increases by 2. So the difference between the first two numbers is 3. The difference between the second two numbers is 5, then 7, then 9, then 11, so on and so forth. Now, whenever that happens, whenever what we would call this the second difference, so this is the difference of the numbers, this is the second difference of the numbers, whenever the second difference of the numbers is the same, that is an immediate giveaway that your rule is going to be something squared, so n squared. So n still represents your term number, so n squared. All right. Well, what is it? Well, if we look at our numbers, so 2, 5, 10, 17, 26, they might not seem as though they have any significance to them, but they do. Let me write out these list of terms, see if you notice anything. 1, 4, 9, 16, 25. What significance do those numbers have? If you said that they were perfect squares, you are correct. Those are perfect squares. 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, and 25 is 5 squared. But if you notice our list of numbers, instead of 1, we have 2. Instead of 4, we have 5. Instead of 9, we have 10, so on and so forth. So it looks like our list of numbers is always 1 greater than a perfect square, right? It's always 1 greater than a perfect square. So we would say our rule is n squared plus 1. N squared plus 1. So this is a little bit more trickier to figure out. And the process by which you would find this equation is not as obvious. We're not going to do many examples like this, but one trick, once again, you can use is this idea of, all right, listing out the differences, but then noticing the differences of the differences, right? The differences of the differences are always the same. So that should be a good giveaway that your rule involves something squared, in this case an n squared. So that would be our rule. That would be our rule. So just a couple of warm-up problems using patterns of numbers. Now let's get to today's lesson. So today it's going to be a very basic lesson to just what a sequence is and just some of the notation you'll see going forward with sequences. So what is a sequence? So a sequence is an ordered progression of numbers, or more a simple way to think about it, a list of numbers. So a list of numbers. That's the most basic way to define a sequence. It's just a list of numbers. So a list of numbers. So it's a list of numbers. So obviously they're going to have some kind of relationship. There will be some kind of pattern to the sequences that we're going to be looking at. So it's a list of numbers, the easiest way to think about it. So let's look at this sequence. This is going to be a little bit trickier. So we have 9, negative 18, 27, negative 36, 45. Well, if we ignore the negatives, it looks like we're just adding by 9 every single time, right? If we ignore the negatives, it looks like we're just adding by 9 every single time. So our next number would be 54. Right, and then 63, and then so on and so forth, right? But it looks like every other number is negative. So we have 9, negative 18, 27, negative 36, 45, negative 54, okay? And then positive 63, and so on and so forth. So if we were to just think about, all right, so these are just multiples of 9. These are just plain and simple multiples of 9. So right off the bat, that would mean our rule, right? Our rule would just be a multiple of 9. 9 times n, right? A multiple of 9 times n. So as you see right off the bat, we use n to represent is the main variable that we use when we talk about sequences and series, and not x anymore. And the reason being is that we want to emphasize this idea that n represents the numbered term, or the term number. So term number. So if n is equal to 2, represents second term, n is equal to 3, third term, so on and so forth. So we got multiples of 9. Now we just have to figure out how in the world do I make every other term negative. Well, there's a simple trick you can use. And then this you can use for any type of sequence where it alternates between positive and negative. And the simple trick you can use is you simply do multiply by -1, but then you put an exponent to it. So like -1 to the n power. Right? So -1 to the n power. And then actually for this one, we would have to do +1. Now, why -1? Well, -1, obviously to get that negative, but why do we put it to an exponent? Well, we put it to an exponent because remember, the way exponents work, it just means you multiply you multiply a number by itself that number of times. So we want to multiply -1 by itself so that it keeps on changing from positive to negative. Because remember, if you multiply a negative by a negative, it becomes positive. But then if you multiply by itself again, it becomes negative. So it just alternates between positive and negative. Now you'll see here, I put a +1 here. Now the reason why I put a +1 here is since our first term is positive 9. I want this to be -1 times -1. So if I were to put a 1 in for n for the first term, right, n equals 1 for the first term, it would be 1 plus 1, which is 2, and -1 squared is positive. This is a trickier problem, so I wouldn't worry too much about it just yet. Down the road, we'll get into more complicated examples such as these, but it's just a preview into the types of sequences we'll eventually get to, more of the trickier types. So let's talk a little bit about the notation that you're likely to see when it comes to sequences. So all the rules we have found thus far for our sequences have been explicit ones, i.e. you can simply find any term by plugging in the term number. So that is one type of sequence equation that you'll see, explicit equations. And the main characteristic that you'll see with explicit equations is this idea that we can plug in any number into it. To get that term on the list. So for example, if I wanted a 50th term on the list, I would plug in 50 into this equation. If I wanted the 100th term on this list, I would plug in 100 into this equation. Okay, and that's exactly what I said. If I want to find the 10th term, I simply plug in 10, so on and so forth. So the notation that you'll see, so we already talked about this idea of having n. So n represents the term number, and here is something new that you'll see. So you usually see A. A is just the name of the sequence, so sequence A. Just when we had like function notation, F was just the name of the function. And you'll see a subscript here, So it's not like it's not like an. It's a and then sub n. So think of a subscript as like being the opposite of an exponent. So instead of being raised, it's lowered. So it's a sub n. Now sometimes you will see it written as like in some kind of function notation, like a of n. You'll sometimes see that written that way. It's just the same thing. Like a of n is equal to 2n is the same thing as a sub n is equal to 2n. So don't freak out. So a sub n. So just take note of that subscript. So a is just the name of the sequence. N is the number that you're plugging in, the variable that you're plugging in for. Okay? So now let's use it. So the subscript in the explicit formula represents the term number, right? We talked about this before. So if n is equal to 10, represents the 10th term, so on and so forth, as well as the number to be plugged in for the given variable. So just like in function notation, x is the variable that you're plugging in for a lot of our sequences, n is going to be the variable that we're going to be plugging in for. So for example, a sub 2, right? So n is equal to 2 would represent the second term. A sub 10, if n was the 10th term, I'm sorry, if n was equal to 10, that would be the 10th term. Okay, so on and so forth. So that's the idea. That's the idea. Whatever that subscript is, that represents the term that you're trying to find. So if your subscript is 3, trying to find the third term. If your subscript is 4, fourth term, so on and so forth. So example 2, find the first 6 terms and the 100th term of the given sequence. All right, so find the first 6 terms. Excuse me. So to find the first term, a sub 1, so that's what we're plugging in for n. So 1 squared minus 1. A sub 2, second term, plugging in 2 for n, so 2 squared minus 1. A sub 3, third term, sorry about that, get that back there. 3 squared minus 1, and so on and so forth. Fourth term, 4 squared minus 1. Fifth term, 5 squared minus 1. Sixth term, 6 squared minus 1. So we can quickly do the math here. So 1 squared is 1. So 1 minus 1 is 0. 2 squared is 4. 4 minus 1 is 3. 8, 15, 25, 30, 24. 24 and 35. So pretty simple. Now the 100th term, would be a sub 100. So 100 squared minus 1. So that would be 10,000 minus 1, so 9,999. So hopefully pretty straightforward. Once again, whatever that subscript is the number that you're plugging in, and it also represents your term. So first term, second term, third term, fourth term. Because remember, a sequence is a list of numbers. So first term, second term, third term, fourth term, fifth term, sixth term, 100th term, if we were to list out all 100 terms. Example 3. Write the first 5 terms for each of the given sequence. Assume n begins with 1. All right. So first 5 terms, so we would do a sub 1 is equal to 4 times 1 minus 7. A sub 2, 4 times 2 minus 7. A sub 3, 4 times 3 minus 7. A sub 4, 4 times 4 minus 7. And then a sub 5. Gosh darn it, 4 times 5 minus 7. So obviously we would evaluate each of these. So I believe, let's see, this is negative 3, this is 1, this is 5, this is 9, this is 13. So you just evaluate each of those. So now next one. A sub n is equal to negative 2 to the nth power. So we've got some exponents here. So a sub 1 would be equal to negative 2 to the first power. A sub 2, negative 2 to the second power, and so on and so forth. So it's pretty, I hope, self-explanatory. This is negative 2 to the fourth, a sub 5, negative 2 to the fifth. So negative 2 to the first is negative 2. Negative 2 squared is negative 2 times negative 2, so positive 4. Negative 2 times negative 2 times negative 2, so negative 8. And then so on and so forth. 16, negative 32. So once again, I hope pretty simple, not too complicated. Remember, the subscript represents, or whatever n represents, not only is that your term number, first term, but it's also the number that you're plugging in for n. Okay? So this one we have 2 n's, but still the same idea. So now, for example, if we wanted to do a sub 1, we would do 1 over 1 squared plus 1. So 1 over 2. A sub 2 would be 2 over 2 squared plus 1. So 2 over 5. And so on and so forth. I'm going to leave these ones to try out on your own. I will be posting the solutions for these example problems, so if you want to try them out on your own and then quickly check out your answers. I think it's pretty straightforward. Not much else to explain. Example 4, find the indicated term of the sequence. So now this is telling us to find a specific term in our list. So a sub 25, Remember, this means to find the 25th term. So this is asking us to find the 25th term in the sequence. So let's do that. To find the 25th term, we simply plug in 25 for n. So -1 to the 25th power times 3 times 25 minus 2. Well, -1 to the 25th power is negative. How do I know that? Well, you can try it out if you want to. The reason why it's negative is because the power is odd. When the power is odd and you're doing it to a negative number, that means your answer ends up being negative. If your exponent is even, so let's say -1 squared or -1 to the 4th power, you end up with a positive answer because of those negatives canceling each other out. And then what do we get here? We get 75 minus 2, so times 73. So it looks like our answer is -73. B is the same thing, except it's asking us for a sub 7. Do watch out here. This plus 1 is in the exponent. This plus 1 is not in the exponent. So just make sure you do that correctly. So for this one, it would be 2 to the 7 plus 1 power over 2 to the 7th plus 1. So just make sure you do those correctly. So once again, you can try that on your own. I will be posting the solutions to these example problems. And then write an explicit formula. So this is back to this idea of just trying to find a rule like we did in the bell ringer. So it looks like these are always going up by 3. These are always going up by 3. So it looks like, so we have multiples of 3, but then, right, multiples of 3 would be 3, 6, 9, 12, 15. So it looks like we have multiples of 3, but they're always going to be 2 less, right? 1 is 2 less than 3, 4 is 2 less than 6, so on and so forth. So it looks like our rule for this one would be 3n minus 2. And we can easily test this out, right? 13 is the 5th term, right? 13 is the 5th term, which means if I were to plug in 5 into this equation, I should get 13. 3 times 5 is 15. 15 minus 2 is 13, so that works. So once again, we can easily test this out to make sure we're right. Does this work? It does indeed. And then the next one, I'll actually let you guys try out B. B is similar to the bell ringer part B. So look at the bell ringer in part B and see if you can do part B for this example. And then once again, I will be posting the solutions to these examples so you can check to see if you did it right. Okay, so in terms of assignment, so this is how it's going to work. It's going to be a little bit different starting with this unit. I'm not going to be posting handouts on Google Classroom anymore. Your homework from now on is going to be Khan Academy for this unit. So Khan Academy will be your homework for this unit. Now, with the Khan Academy, I will be posting a couple of videos as well. Do you have to watch the videos? You do not have to watch the videos, but you do have to do the 4 or 5 question assignment that usually comes with the problem set that usually comes with the lesson. So you do have to do that for credit. So you do have to do that. You do not have to watch the videos. The videos are helpful, so I would actually watch them if you try out the problems and they don't make any sense. So I would go back to the videos if they don't, if the problems don't make any sense. So that's how this unit is going to be working out. Khan Academy, I will not be posting those handouts anymore. But as usual, always let me know if something confuses you or if you have any questions or concerns regarding that. So that should be it for today's lesson. Obviously, the deadline for the Khan Academy, I will be posting that on Khan Academy, so you'll see exactly when they will be due. Otherwise, I hope you guys are staying safe. I hope you guys are staying healthy. And I hope you guys enjoy the rest of your days. See you later.